Hello, how you doing? This is Mike again. So we are going to expand on a problem that I did just prior to. It was a volumes question, and I've changed it ever so slightly because in our last problem we revolved the same structure about the line y equals to 4, and in this problem we're going to rotate about the line x equals to 4. So it's going to be slightly different, but we'll see that just by changing the axis of revolution, it dramatically changes the outcome of the question, even the process in which we're going to go and tackle this question. So if you want to go back, there's another question I put on here. It's going to be my question number 4 from my Calculus 2 volume series. You can watch that first, but I'm just going to quickly go through graphing this scenario. So we have the line x cubed over 2, the curve x cubed over 2 in the positive one axis. So it's going to look something like this, like that. It's bound by y equals to 0, which is the x-axis, and then it's bound by x equals to 2, which is the y-axis. So it's the vertical line vertical line x equals to 2. So it's going to look something like this. Very patriotic. So we have where is it? Here we go. So we have something that looks like this right here. So this is our line x equals to 2. So this is the critical point 0, 0. It's the origin. This exists at 2, 0. And since this is the line x cubed over 2, then this will be the point 2, 4. 2, 4. So now if we were to rotate this, so I'm going to rotate this, I'll rotate in gray. Rotate about the line x equals to 4. So this is the line x equals to 4. We're rotating about this line, so I'm going to put my little corkscrew up on top. So this will give me something that looks like this. So trying my best to be as symmetric as possible. So here, here, and here. So when I look to evaluate this question, I'm just going to move this up to the top here. When I look to evaluate this question, there is a special method that I'm seeing that will definitely make this problem a lot easier. I tend to like integrating with respect to x. I tend to like to integrate with respect to x. And since I have a vertical line of rotation, if I used the washer method, I'd have to integrate with respect to y. But the shell method is actually using the opposite. It uses the opposite idea. So if you have a vertical line of rotation with the shell method, you're going to integrate with respect to x. So a vertical line of rotation for shell, you integrate with respect to x. So I tend to gravitate my methods depending upon how I can integrate with respect to x, especially if my functions are defined in terms of x, because otherwise I'd have to resolve this, and this would give me x equals to the third root of 2y. I'd rather just go ahead and work like this. So the shell method is the method that I'm thinking of right now. So when I think the shell method, I'm going to calculate a volume on some bounds. So we're going to have 2 pi times some value of the radius times some value of the height of your shell, and we're going to integrate with respect to x because it is opposite of the type of axis line you have. I'm sorry, hope I said that in a way that wasn't too confusing. I'm integrating with respect to x because my axis of rotation is vertical. My radii of my shell. So let's go ahead and look at a shell here. So I'm going to use this gray. So this is the shell that I'm putting in. So it's like a Coke can without the top or the bottom. So I put my Coke can in from the very, very top, and I have my heights, which exist just like this. So it's like putting my Coke can in, and I get my heights that look like this. So notice my radii is still perpendicular to my axis of rotation, and this is the radius. I'm saying radii, I should be saying radii is plural for radius. I only have one radius, so I should be using radii, but sometimes I say it incorrectly, so I apologize about that. But my radius is still perpendicular to my axis of rotation, but with shell method, your radius is going to be indicative. Your radius is going to be indicative of the type of integration. So since I have a horizontal radius, I will be integrating with respect to x. The other two are opposite. So there's a lot of different ways you can go about remembering how to go about doing this. I just look at my axis of rotation with shell. If axis of rotation is vertical, integrate with respect to x. If I'm integrating the shell method using shell method, if my axis of rotation is horizontal, I integrate with respect to y. So now we have to figure out what is the radius of my shell. My radius is this guy. So I'm going to go ahead, I'm going to write the radius over here. I tend to think a little bit better on this end. So this is my radius that I just drew right here. So this is my radius r. When I look, there is a total value that exists between the y-axis and my axis of rotation. This is a value of 4. Hopefully we can all see that from the y-axis to my curve, this is a value of x. No matter where I am from the y-axis to the curve, this is a value of x. So if my shell was down here, my radius would change. My radius would change. This would be my new radius. So hopefully we can see that if the larger value is 4, the smaller value is x, then the radius would be equal to 4 minus x. This value here is going to be 4 minus x. I just lost some, so I don't know why it just decides to delete random stuff on my screen. It's just sabotaging me. So my radius is actually going to be equal to a value of 4 minus x. The height is going to be this guy. The height is going to be this guy right here. So that's going to be my height. My height is going to be just a value of y. My height is a value of y. But y is equal to x cubed all over 3. So where am I going to be integrating? I'm going to be integrating from 0 to 2, from 0 to 2 of 2 pi. My radius is going to be a value of 4 minus x, and my height is a value of y, which is going to be x cubed all over 3, and I'm integrating with respect to x. I'm integrating, with respect to x. I'll do this in white. It's a little bit easier to see in white. So we will have the volume being equal to, I'm going to pull the 2 pi out in front, integral from 0 to 2 of 4 minus x times x cubed all over 3, all with respect to x, and I'm going to pull that 1/3 out as well. I'm going to go ahead and pull out the 1/3, integrating from 0 to 2. Distributing the x cubed, we're going to have 4x cubed minus x to the 4th. Integrating with respect to x. This is a nice integral. Keep that 2 pi over 3 out in front. So I'm going to have 4x cubed over 4, or x to the 4th, minus x to the 5th, all over 5, bound from 0 to 2. So I just integrated these two portions right there. I'm going to go ahead and plug in my top bound. So I'm going to have 2 to the 4th, which is 16, minus 32 fifths. Subtracting off my lower bound, I just show this, just never to forget. It just helps me not forget. So this all goes to 0. So we have 16 fifths minus 32 fifths, and that's going to give us a value of 48 fifths. 48 fifths. So we're going to have 2 pi over 3 times 48 fifths, like such. And this will simplify to 32 pi's all over 5. So just to make sure I'm correct, I'm just going to check myself. And I feel really good about 32 pi over 5. So noticing that so many things about these questions can change, you have to be very particular about identifying your radius and your height. I really like the shell method. I really like the washer method. I like all the methods. I just become very fluent with them. Sometimes I work through problems and then I arbitrarily change things to see how easily I can amend my own protocol. So to evaluate the new problem, very rarely do I change the boundaries, but I might change the axis of revolution. I usually change that relatively pretty often, but I'll keep these the same, otherwise the problem gets really tough. But hopefully this helps you work through these types of problems. So just practice and repetition and seeing all the different ways to solve this. Again, 3 consistent ways: the shell method, which is one of my favorites, the washer method, another favorite, as well as the disk method. Hopefully these videos are helping.